Fire. It's one of those things we see all the time. It's one of our oldest tools, and honestly, it's just mesmerizing. But have you ever stopped to think about what's actually happening in that flickering flame? It's way more than just a pretty light. There's some incredible science going on. So we're going to dig into a question that sounds super simple, but is actually going to take us to some pretty amazing places. What is fire, really? And why is it so hot?
Yeah, that's the big question, isn't it? Why is fire hot? It seems almost childishly simple, but trust me, the answer is anything but. To figure this out, we're going to go on a journey that starts with basic chemistry and ends, believe it or not, in the heart of the stars. So, let's dive in.
All right, let's get right to it. Why is fire hot? Well, the first thing to get your head around is that the heat you feel, it isn't just magically created out of thin air. Nope. That energy was already there, just locked up tight inside the fuel, waiting for its moment to break free.
A really good way to think about this is to think about the food we eat, right? We eat an apple or a sandwich to get energy for our bodies. Well, fire does the exact same thing. It eats its fuel. When a piece of wood burns, it's going through a super fast chemical transformation. All the bonds holding its molecules together break, and boom, that stored energy is released as the light and heat we know and love.
Okay, so fire is really just a chemical reaction. You gotta ask, what's the recipe? What do you need to cook up some flames? Turns out it's surprisingly simple. You only need 3 key ingredients. And this is it, the famous fire triangle. It's a classic for a reason. First up, you need fuel. This is the what that's gonna burn. Could be wood, gas, even the wax of a candle. Next, you need oxygen. That's the gas all around us, making up about 1/5 of the air we're breathing right now. And number 3, you need a source of heat. You need that initial spark, that little bit of energy to get the whole party started. And here's the crucial part. You need all 3. Take away the fuel, the oxygen, or the heat, and poof, the fire is gone. So this whole process, this triangle of fuel, oxygen, and heat, it has a proper scientific name: combustion. That's all it is, really. A super fast reaction between a fuel and oxygen that unleashes all that stored up energy. So this is a really key takeaway. Fire isn't a thing. It's not a substance. It's the result of a process. You're watching combustion happen right before your eyes. So we've covered the how, the invisible process. But what about the part we can actually see? Let's talk about the flame itself. What is that glowing, dancing thing anyway?
Okay, so the flame, that's where all the action is. The heat from the reaction turns the solid or liquid fuel into a gas. And it's inside that shimmering column of hot gas that the fuel and oxygen molecules are just smashing into each other. They're breaking apart, creating new molecules, and releasing all that energy we've been talking about. You are literally watching chemistry unfold in real time. How cool is that?
Now, we get to one of my favorite parts, the color of a flame. I mean, we see all these beautiful reds, oranges, yellows, and even blues. But those colors are not random, not at all. They're actually clues. They're telling us a detailed story about what's going on inside that fire, its temperature, its chemistry, the whole shebang.
So where do these colors come from? Well, it's basically down to 2 main things. First, you've got that classic yellow and orange campfire glow. That's caused by something called black body radiation. What's happening is tiny little particles of unburnt carbon, we're talking about soot basically, get so incredibly hot that they just start to glow. Think of an electric stove element turning red hot. Same idea. But then you have the blues, and that's a whole different story. That comes from something called spectral band emission. This is where specific molecules get so energized by the heat that they release light, but only at very specific wavelengths, which we see as blue or sometimes even green.
And this is a perfect way to see those 2 effects in action. On one side, you've got a candle flame, which is a diffusion flame. Here, the fuel, the wax vapor, has to kind of haphazardly mix with oxygen from the air around it as it burns. It's a messy, inefficient process, and it creates a ton of that soot we talked about. And that soot glows yellow. But on the other side, you've got your gas stove, which has a pre-mixed flame. Here, the gas and oxygen are all mixed together before they even ignite. The result, a much cleaner, more complete burn. There's almost no soot, so you don't see the yellow glow. Instead, you see that clean blue color coming directly from the excited gas molecules. Okay, get ready for your mind to be a little bit blown. We're all taught that blue flame means hotter, right? Blue is hotter than yellow. Well, for a candle, that is completely 100% wrong. Check this out. The blue part right at the base of the wick, that's actually the coolest part of the flame, around 600 degrees Celsius. The bright yellow part in the middle is way hotter. And the hottest part of all? It's the almost invisible tip, which can reach a scorching 1400 degrees.
It just goes to show it's all about where the chemical reaction is happening most efficiently, not just the color. All right, so we've got the basics down for your everyday flame. But, science, we can't just leave it at that. We have to push the boundaries. So let's take a look at what happens to fire in some really extreme conditions. And let's start with something that sounds like a total contradiction, a cool flame. I'm not kidding, you heard that right, a flame that's cool. It was first discovered way back in 1817, and it turns out that under just the right conditions, the right pressure, the right mix of fuel, you can get a reaction that produces a flame that burns at only 120 degrees Celsius. To put that in perspective, that's just a little bit hotter than boiling water. Incredible.
Okay, so from the coolest flame possible, let's jump to the complete opposite end of the spectrum, the absolute hottest. The most intense chemical flame ever created came from burning a wild-sounding compound called dicyanoacetylene in an atmosphere of pure ozone. And the result was just staggering. A flame that reached almost 5,000 degrees Celsius. That is nearly as hot as the surface of our sun. Just wow.
So, we've pushed the limits of temperature, from cool to insanely hot. But what about pushing the limits of the environment itself? What do you think happens to a simple flame if you just take away gravity? Think about it. Here on Earth, hot air rises. That process is called convection, and it's what gives a flame that classic pointy teardrop shape. It's constantly pulling cool, fresh oxygen in at the bottom and pushing hot exhaust up and away. But what happens in space, like on the International Space Station? Well, there's no up for the hot air to rise to. Convection just stops. And as NASA found out, the flame completely changes. It becomes a perfect little sphere. It also gets dimmer, and because there's no soot, it burns with a clean blue color. It's a totally different beast. So we've looked at fire on Earth, we've seen it in extreme lab conditions, and we've even taken it to space. But the story of fire, the story of combustion, it's so much bigger than that. It's a story that's written across the entire universe. I mean, look up at the night sky. Our sun and every single star you can see, they are, for all intents and purposes, giant raging balls of fire. But this isn't the chemical fire we've been talking about. This is something else entirely. They're powered by thermonuclear flames. Deep in their cores, the gravity is so immense, it's literally crushing atoms together, fusing hydrogen into helium. That's nuclear fusion. And the energy it releases is just astronomical. That right there is the engine that powers the entire cosmos. So there you have it. We started with a really simple question about a campfire, and it took us all the way to the nuclear furnace at the heart of a star. The fact that the same fundamental physics can explain both a tiny candle flame and a giant cosmic explosion is it's a powerful reminder, isn't it? It really makes you wonder, what other incredible, profound secrets are just hiding in plain sight all around us, just waiting for someone to ask the right, simple question?